Thank you very much, Thierry. It's a pleasure to have you here. Can you describe your research field?
So I work in biophysics, broadly speaking. So I'm a physicist, but working on biological systems. The reason why I think this is relevant is because statistical mechanics is the science of explaining the whole out of its parts when these parts are interacting. And obviously, if you think about living beings, they're made of many small interacting units, molecules, cells, organs, that interact with each other, communicate with each other, and as a whole, behave in a way that maybe it would be hard to predict from just looking at single units. And so statistical mechanics is a good tool for doing this, and it's a relevant concept across many subfields of biology, and this is why I work on different topics. One of them is neuroscience, which is the one for which I'm here. But I also work on immunology, which is also an interesting system in which there are many units, your lymphocytes, your white blood cells, collectively fight infections. And also work on collective behavior. For instance, the very interesting phenomenon of bird flocks, so birds flying in the same direction in a very coordinated manner by interacting with each other.
Well, building on that, you have been using the maximum entropy principle to describe the behavior of various biological phenomena at different scales, from DNA, proteins, and networks of neurons, of retinal ganglion cells, and even for flocks of birds. So can you briefly describe the studies that you have been conducting?
Okay, so the maximum entropy principle is a somewhat technical word to encode a fairly simple idea, and it's an idea from the point of view of the modeler. So I'm a theorist. I'm interested in building models for describing nature and collective behavior in that sense, in that particular case. And when you want to build these models, there are two ways of doing it. There's the traditional way, which has been very successful in physics, but also in other fields, which is to think of some principles, some macroscopic laws of interactions, and write them down and then see what happens in terms of predictions, in terms of observables, and then compare those to the data. And there's another way which has been gaining a lot of traction in the past decade or so, even more, which is to try to build our models directly from the data that we collect about the subject. And so the maximum entropy principle is just, if you like, a tool for doing this in a fairly efficient way. So it goes like this, that it postulates that there are some observables that we care about, that we would like our model to reproduce. We start with what we really want our model to reproduce. And then it postulates that among all the models that could actually reproduce the simple observables that we picked, one of them is as random as possible. So in a way, it makes us quite agnostic. We don't want to make too many assumptions about the model. And that's the one we pick. We're not claiming that it's necessarily the best one, but it's a formula for having the simplest one in some sense. And then one can predict some observables that we did not impose that the model has to see whether it does successfully. Another reason why these models have been interesting to me is because in many cases, from the mathematical point of view, once you actually write down the models these correspond to, they look very much like models that are very familiar to statistical mechanics. And in particular, a whole class of models of magnetism that help explain spontaneous magnetism, and also some models which are very relevant in modern condensed matter theory, for instance. So this allows us to make an explicit bridge between physics and the physics methods and the biological systems.
Well, thank you very much, Thierry. That's all.
Okay.
Thank you very much.